second session of the day. Should we, the what session of the day? So yesterday I introduced you to the whole idea of devising a Markov chain whose invariant distribution was some posterior, if we were doing some Bayesian modelling, that we were interested in sampling from, to allow us then to perform inference, whether it's predictive inference or posterior inference over estimates and so forth. And the key idea was that a sufficient condition for a Markov chain to have an invariant distribution was this notion of reversibility. And we built up a transition operator that was based solely on this sufficient condition. And we arrived at the Metropolis and then the generalized version of the Metropolis algorithm, the Metropolis-Hastings algorithm. And the whole idea of defining a proposal distribution which is completely arbitrary, and then having an acceptance probability which is a function of the target distribution computed at the proposed point in the variable space and the current point in the variable space, and the value of the forward and backward proposal density. Right, so that product form gave us our overall kernel to devise the Markov chain. And this is all great. We then looked at a number of issues, practical issues, which needed some theoretical basis and a framework in which we could start to build up quite a robust methodology. And we looked at things such as product kernels to divide the space that we were trying to sample from into perhaps a number of discrete blocks that made some sort of sense to allow us to progress the whole idea of sampling. And we were able to show that if the components of the product kernel themselves were reversible and then had the particular invariant distributions, then the overall product had the joint probability distribution as the invariant distribution of the overall chain. And likewise, if we took a mixture of kernels whose invariant distribution was the same, then we could define some sort of sampling scheme that perhaps had local and then global scales to allow us to move across regions of very low density or high energy barriers, if you want to think in a physical term, which would allow us to sample at the correct frequencies from perhaps various modes in the distribution and so forth. We then looked at Gaap sampling, and we're now convinced that Gaap sampling is nothing more than a special instance of the Metropolis-Hastings algorithm, where the proposal distributions are in fact the exact conditional distributions of the target that we are wanting to sample from. We found that there was a very nice trick called data augmentation, where we could include some ancillary or some auxiliary variables, which again had nothing to do with our statistical model, but they expanded the overall distribution which we were sampling from and allowed us, in some cases, to obtain exact conditionals. And the example I gave you, of course, was the probit model, where we can have this very nice Gaap sampling scheme, sampling from a multivariate Gaussian for the parameters of the covariates, and then sampling from a series of unidimensional truncated Gaussians. Now, of course, the problem there was that the auxiliary variables and the variables of interest were correlated, and so potentially we could get very poor mixing. And then we started to look at the issues of, well, how do we select the proposal distribution when we have strong correlations in our sampling space and so forth. And we started to look at the idea of adaptive proposal distributions. And I spoke about this idea of exploiting a discrete version of a diffusion process whose invariant measure was related to the density of interest that we wanted to be able to sample from. And what was really very nice about this construction here was that the proposal distribution was no longer completely ignorant of the target distribution that we were interested in, but it now had some function of our target distribution appearing in the mean function of this proposal density, which would just be a multivariate Gaussian. And of course, this would then accelerate convergence. It would also improve the overall sampling in the stationary regime. So this was great. However, the problem that we found was that we had this isotropic scaling of the diffusion, and so we still arrived back at the same old problem that although we had a much smarter mean function, at the end of the day we were still having a uniform scaling across all of the axes of the space that we want to sample from. And we looked at the sort of cigar-shaped two-dimensional Gaussian, which had a very strong correlation coefficient, and we showed it's very clear that this is going to perform poorly in that situation. And of course, the way around that would be to use this preconditioning that we spoke about. And if we had some oracle, right, where we could just pluck the correct preconditioning from, then we would be done. But the question is, well, how do we actually set it? And how do we tune it in the various phases that the Markov chain would find itself in? And that was an open question. So the last thing that I want to talk to you about today is, the last thing I wanted to talk to you about yesterday but didn't get a chance to, so I'm going to talk to you about today before I move on to some other things. There's another adaptive scheme which surprisingly is not really that much, hasn't been really adopted in applied statistics as it probably should have. It tends to be adopted in machine learning, but I question how rigorously it's actually adopted in a lot of applications in machine learning, and that's the Hamiltonian Monte Carlo method. Now what we're going to do here is I'm going to try and describe it in a way that's very intuitive so that you get the basic ideas from a sampling perspective rather than going off and pretending I'm a physicist and that you're all physicists and talking about Hamiltonian dynamics, although I'm not going to be able to get away from that. But really I want you to leave you with a good feeling and understanding for what's going on here, and hopefully enough interest to follow up the underlying theory and potential methodological developments for it. So again, we've got a target density. This should be pi. I'm now calling it p of theta. And we're going to use the data augmentation trick. We're going to introduce an auxiliary variable, p. Now again, this auxiliary variable is completely ancillary to our model. And we'll say that the density of p is, again, a multivariate normal with some mean of 0 and a covariance structure m. So we'll just leave it at that. Now, if we then take, so if we just use the same notation again, that calligraphic L theta corresponds to the log of our target distribution over the variables of interest theta, then we can write the negative of the joint log density of our variables of interest and our auxiliary variables in this form here. So we have the log, the negative log of our target distribution, and then we have the negative of the log of this multivariate Gaussian. So we have this determinant of the covariance matrix of the auxiliary variables, and then we have this quadratic term based on this Mahalanobis metric here. Now, I'm going to have to pretend that... How many of you studied physics? Okay, that's comforting. How many of you studied engineering? Okay, this is going to be fine. And how many of you are just far too smart and decided to study mathematics or something like that? And how many of you studied computer science? Okay, I'll go really slow for you guys then. Right. So, for the computer scientists, what I would like to do is take you back to A-level, O-level, secondary school physics, and I want you to think about potential energy and kinetic energy, okay? That's it. So, potential energy when I lift this off the table, and then the kinetic energy when it falls and it gains velocity. Now, I hope that all the computer scientists haven't fallen out with me and are starting to bear a grudge. Just being a professor of computer science myself, I'm poking fun at myself as well as you. So, we could think of this in a physical way. Let's think of theta as, well, what is theta? Theta is a point in some space, right? It defines a point in some space. So when we have kinetic energy, right, potential energy, we're defining some object, right, with its mass and the field that it's actually in, right, and a set of coordinates. So I'm going to say that those coordinates will correspond to theta. Right, so, and that's all theta is. It's just a point in some coordinate system. Okay? So, by some stretch of the imagination, we could say, well, this function, calligraphic L, is just a function of the coordinates and nothing more. So we could actually look at this and say, well, we could consider this as a potential energy. Right? So a unit mass and some field or whatever defined by L, that's the potential energy of some system. Everyone happy with that so far? Yeah? Now what about this term here? Well, n isn't a function of n, it's just a constant. This is a constant, so we could just ditch this, right? This is just invariant, so we can ignore that. But the next thing that we see is this quadratic term here, based on our auxiliary variables. Okay, so let's go back to schoolboy physics. Momentum is equal to mass times velocity. Velocity is the derivative of space with respect to time. So this is our point in space. So let's just say that P is momentum. Right? Just give it a physical interpretation, right? So P is a momentum associated with this coordinate system. Right? So velocity, so theta dot, d theta by dt, times mass. Yeah? So if I replace P by theta dot times m, what does this boil down to? A half? You're far too clever for me. What is it actually, what do they equate? What's the equation? Let's go a bit slower. A half m theta dot squared, which of course is just kinematic energy. Okay, so what we've got is this equation, which is the joint likelihood of our target, log likelihood, negative log likelihood of our target distribution and this auxiliary variable. But let's pretend we're physicists and we could say this is some potential, and this is a kinetic energy associated with a particle, right, moving through this coordinate system where theta is a point in the coordinate system. P is a momentum, and therefore M is a mass matrix, it's a constant mass matrix. So overall, this is the total energy of a system, closed system, right? Now, for those of you who did study physics, and for those of you that didn't, this is still pretty straightforward. But because this is the total energy of a system, because there is potential, there is kinetic energy, there is dynamics, right? So particles will be moving because of the field and because of the action of the field on the mass of these particles. And so we can describe the dynamics, right, of a particle in this system here by what? By really state-of-the-art 17th century physics, right? Just Newtonian physics. And then we go forward a century, and Hamilton and Lagrange rewrote Newton's equations in a different form, but basically described the same dynamics, but in a different form. And this is the form here. So d theta by d tau, where tau is some notion of time, is what? This is our velocity of a particle moving through this little coordinate system. And what Hamilton showed was that we can write the velocity of the particle going through this system in terms of the partial derivative of the total energy of our system with respect to momentum. And of course this just turns out to be P divided by M, which of course is velocity. And the sort of conjugate equation was that the rate of change of momentum is just equal to the negative of the partial derivative of this expression for the total energy with respect to position, with respect to theta. And of course this is just going to be the gradient of the potential field. So the dynamics, right, of a particle in this field can be represented by these systems of partial differential equations. Okay, now just hang in here because there's a happy ending to this story, but I need to give you this this kind of background, which is really quite interesting. So that's the dynamics. The dynamics, so this is the velocity, the way in which particles will move in this field, right? The way that the kinetic energy and potential energy are transferred are all described, right, by these systems of differential equations. Now, what are the properties of these dynamics? Now let me just also point out that everything that I'm putting on here, right, is relevant to the whole scheme of devising a sampling method that is improved upon what we've done before. So everything in here that I'm presenting in a kind of physical, from a physical perspective, is going to be directly relevant to the construction of an MCMC scheme employing these underlying principles. Well, the first thing is that trajectories that a little particle would move along, right, under this, the influence of this potential field, describe contours of constant energy in the space defined by theta and p. Now, theta and p is called the phase space. Okay? So we've got the coordinate system, theta, and then we've got the variables that describe the dynamics, the velocity p. So theta and p describes the phase space. And so a particle moving in this phase space, so just remember, as a particle moves from one point to another, right? Both potential changes and kinetic energy changes. So theta and p, right? So it's going to be moving in this theta p space. So the trajectories that this little particle moves along are constant, have constant energy. So at every point, theta p, right, the particle moves to theta prime, p prime, the total energy remains the same, right? So in other words, the total energy, and this total energy was named after Hamilton, right, who developed this theory of dynamics. So the trajectories, the dynamics then conserve the Hamiltonian. They conserve the total energy, so it's a conservative system. So that's the first thing, right? So any movement, right, the energy is conserved. What does that mean? Let's just flip back to pretending we're machine learning or statisticians. Well, what that means is that any proposal that moves from one point theta p to theta prime p prime, it means that the likelihood, or the distribution, the joint distribution of theta and p is always going to be the same. So it's going to be moving along isocontours of equal joint likelihood. Okay? So that might be useful. Why do you think that might be useful? Remember the problem we had when we had the cigar-shaped target density, and we had the spherical proposal. If we make a proposal from here to here, what happens to the density at this proposed point compared to the current point? It goes down. Now, if somehow or other, and we're going to get to how we do this, the proposal that we actually make follows these dynamics, then the Hamiltonian is conserved, the total energy is conserved, and therefore, what? The density is the same, and that means that the acceptance probability is going to be 1. Okay, so this sounds good. You agree? You don't agree?
I'm confused.
Oh, why are you confused, son? I don't want you to be confused.
Well, if you're going outside the cigar shape, then why will be accepted?
Remember that the conservation of the Hamiltonian is in the phase space. It's in the space of theta and p. So what we're looking at is just the space of theta, right? But what we're trying to do is build, remember the data augmentation trick? We're trying to build a Markov chain on the joint space. So on the joint space, right, we may well be moving into this region in theta, but in theta and p, we're actually moving on what's happening is in theta p space, this is a dot, isn't it? In theta p space, that little proposal is moving around like that. So it means that we would accept that with probability 1, despite it actually moving here, or being proposed to move here. Does that help? Have the scales fallen from your eyes? Well, hang in there. Any other confusion, or anyone else got any questions just to clarify? Yes?
I was wondering whether you would create cycles with it, maybe, if you don't convert.
Yes, we'll get on to cycles, and I'll actually show you some cycles. Good point. You obviously studied physics. Yeah. Any other questions? So I think if we spend the time here, once we get on to the differential geometric stuff, then we'll be able to sail through it. Everyone else clear? Yeah?
So this depends on the
It has to be sufficiently large to ensure that this is always constant. And under these dynamics, the change of P and the change of theta will ensure that this is invariant.
So if P, if the set in the last term is too small, then we cannot make this jump.
I'm not sure why. Because all we're doing, this jump, all this is doing is following the dynamics defined by these differential equations. So this is just motion.
If it is discretized.
We're not talking about discretized just at the moment, okay? Right, so we're good. Okay, so this conservation of the Hamiltonian relates to an acceptance probability of 1 when we're doing this continuously. So this looks good. The trajectories are reversible. So in other words, we have these mappings that are injective. So if we move in phase space, so it's theta p space from here to here, then applying the dynamics, we would follow the same path, get back to where we first started. Is that going to be useful? Reversibility? Why? Come on, you were shaking your head with great enthusiasm there. So, I just said that. So I mean, what is the implication of that? What is the whole basis of a Markov chain having an invariant distribution? Please. It has to be detail balance. It has to be reversible. That's the sufficient condition. And if we've got that, then we know that the invariant measure exists. So the fact that these trajectories are reversible means that we potentially would have a proposal process which would have in itself an invariant measure. So this looks good. So already we've got something that says, look, it looks like if we use these dynamics somehow or other to define a Markov chain, because the trajectories are reversible, it's going to have an invariant measure. And because the trajectories in the phase space, in theta p space, conserve the Hamiltonian and therefore are moving along isocontours of the joint density, then that means that if we can do that without any error, the acceptance probability is 1. So this is looking promising. So the other thing, the other characteristic is that, and this becomes more important once we start talking about all of this stuff in Riemannian manifolds, is that the trajectories that are followed, right, and therefore the flows, and therefore the mappings associated with that, will preserve volume elements in the phase space. If we took a little volume element in theta p space here, right, and then we perform this mapping, right, so the mapping again is the solution of these differential equations, so it defines a flow in theta and p. Right? So we might have a little volume element. So typically in the physics books you see the nice little cat's face and then it gets stretched and so forth. But I'll just draw a box. Right? So there's my little volume element here. And then under the mapping defined by the flow, it ends up something like, it's probably going to look like a box again. Okay, and maybe it looks something like this. But the key point is that despite that distortion of the mapping, the volume is maintained. And this becomes important when we define our Hastings ratio and our acceptance probability. Because if this volume preservation was not a facet of the underlying dynamics, then we would have to correct right, for that change in volume, because that then changes the measure. But we don't need to worry about that because volume is preserved. So our acceptance probability is just going to be what we've seen previously. It's not going to require any Jacobian to correct for change of measure and so forth. And so what it turns out is that because the mapping under these dynamics is reversible, then as we alluded to, we can then construct a transition operator for a density which is basically this here, which of course is just the joint density of theta and the auxiliary variable p. And so if we can devise our Markov chain which has this as its invariant distribution, and we sample thetas and p's, then we know that the thetas are going to be marginally distributed according to p of theta, and the job is done. But there's a tantalizing prospect that we might actually have a proposal scheme and an eventual Markov transition kernel which might give us acceptance probabilities of 1. Well, we had that in the Gaap sampler, but then the Gaap sampler, in the case of the cigar-shaped bivariate Gaussian, was limited by the level of correlation structure. So we need to see if this scheme here is actually going to be able to get around that problem, in that rather than making small steps and accepting them with probability 1, we can make large steps and accept them with probability 1. And that's exactly what we want. We want to make large steps so that we can cover the overall space. We can reduce the level of correlation once the chain is converged to ensure that our Monte Carlo error is tightly controlled. Okay, so this looks promising. So let's now try and use these Hamiltonian dynamics to try and define an overall transition kernel. So the first thing that we should notice is that the mapping, now when I say the mapping, what I'm saying is that I'm using these dynamics, right? So I'm solving these equations so that I can go from theta at t to theta at t prime, right? It's deterministic. So this is a system of nonlinear differential equations, and the solution is deterministic. So that means that the proposal associated with solving these equations and then moving from one point in phase space to another is just going to have a Dirac measure for the proposal distribution. Okay? So unlike the random walk, where there's the density is, say, a Gaussian, right? Here, because this mapping is deterministic, then we just have a value of 1, mass of 1 for the proposal distribution. So I alluded to the fact that if the mapping preserves the volume element, right? The Jacobian of that mapping has a unit determinant. I think you should all know that. And that means we don't need to scale the Hastings ratio in any way. And that's good, because trying to figure out what the determinant would be for the solution of these equations would be a bit of a headache. So we can ignore that completely. And it turns out that because things are reversible, then detailed balance would be satisfied if we devised an acceptance probability which was just equal to the minimum of 1 and then the exponential of the negative of the Hamiltonian at the proposed point plus the Hamiltonian at the current point. But of course we know that these are both the same, and so this is 1. But once we come to actually solve these numerically, then of course we start to induce errors, and the energy will no longer be exactly conserved because of numerical integration, and therefore there would be some error here, which is induced by the numerical integration of the solution to obtain the solution of these equations. But in the continuous case, if we can solve these analytically, then the Hamiltonian is preserved under these dynamics, and so the overall acceptance probability is always going to be 1. Brilliant. Let's just stop there, because I've probably condensed quite a lot into one slide. Any questions or any deep insights you want to impress us with? I think if anyone's got any questions, or you want some clarification, please ask, because for a lot of us, this is not straightforward stuff. But it's really cool stuff. You can publish lots of papers. Yes?
So, lambda diffusion was also solving some differential equation, right?
Mm-hmm.
So I'm not clearly seeing how these two things are related.
Okay, so, well, first of all, they're not related. Right, so the Langevin diffusion is defined by a stochastic differential equation. The dynamics here are defined by a deterministic system of ordinary differential equations. Yeah? Any other points of clarification you want? Are we all happy to go on? Does the silence mean yes? Does the silence mean no? It means no.
So if this is completely deterministic, how is this a random walk?
It's not a random walk. It's a deterministic walk. So
how's that sampling?
it's not sampling. And that's a great question. And that's going to lead on to the next point. So the key point that our colleague from the US has just pointed out is that everything here is deterministic. The proposals are deterministic, but what we want to do is something that's completely stochastic. We want to define a Markov chain, a Markov process. So there's something not quite complete with the overall story, which we'll finish now. But before we get on to that, as I said, these are a system of nonlinear ordinary differential equations. If the target distribution is a Gaussian, then we can solve these. Right? And it just turns out to be an exponential operation to define these deterministic flows. But again, for the majority of target distributions of interest, we're not going to be able to solve these analytically. So we need to use some sort of numerical integration method. And there's lots of numerical integration methods that we could use. However, this particular system is very special, and it's special because there are certain properties that have to be maintained. And the properties are that the total energy has to be conserved, that the trajectories or the flows have to be reversible, and that the volume elements have to be maintained. So whatever numerical integration scheme we use, we have to make sure that they preserve reversibility and they preserve volume, okay? And if possible, conserve the total energy. So that then restricts us to a class of numerical integrations. It restricts our choice of numerical integration schemes that we can employ. So as I said, because we need to retain reversibility to ensure that this overall Markov process is going to have an invariant distribution. And we want mean, volume preservation isn't necessary. It's not even sufficient, but it's very convenient. So if we can have that, then it's going to save an awful lot of heartache. So it suggests a particular class of numerical methods. And there's a whole field of research on numerical methods for the integration of Hamiltonian dynamical systems. And we look for a class of integrators which are called symplectic integrators. And these symplectic integrators preserve certain geometric properties of the underlying system. Now, it's a fascinating area. I'm not going to go into the details of it, but suffice to say that a symplectic integration system, right, so if it's symplectic, then two properties that it will satisfy are preservation of volume and reversibility. And the sort of simplest and best, well, actually it's not the simplest. There are simpler numerical integrators that preserve volume and are reversible. But the one that has been, that is used without any thought at all in the literature is what's called the leapfrog integrator, or the Stormer and Verlet integrator. And it's similar to, well, it's not similar to an Euler scheme, but you can think of it as a scheme where what we do is we take half a step. So we're going to solve for P, right? So we're going to discretize this. So we're going to take P at tau plus 1 is equal to P at tau plus this gradient term here, right? So we take a half step, right? Tau plus some integration step size epsilon divided by 2 is just going to be this here, right? So that just comes from the discretization of these differential equations here. Then we discretize these differential equations and we take a full step, right? So we integrate numerically, right, to tau plus epsilon, and it's going to be equal to the current value of theta, and then this gradient term, right, which again, just if you remember, just comes from this partial derivative here. Okay? So we're now using the momentum at that, the updated momentum at this first half step. And then we update the momentum again by another half step to take us to the same integration at tau plus epsilon. So that theta and P are both now updated at tau plus epsilon. Now, as I said, there is a huge amount of work on developing integrators for Hamiltonian systems which are symplectic and have certain order characteristics in terms of the error induced in the total energy, and also in their convergence and their stability and so forth. But I think that takes us out of the realms of really what we're interested in. So suffice to say that this little scheme here, this little numerical integration scheme here, does pretty much everything that we want. So the reversibility of this scheme just follows very naturally, and we note, for example, that the Hamiltonian is symmetric in P. So whether it's P or minus P, this is always going to be the same. Right, so this holds. And the other thing, of course, is that because theta and P only appear in the integrator in additive form, not multiplicative form, then again, reversibility is guaranteed. And it's a fairly straightforward back of a fact packet or back of an envelope piece of work, just to actually take a forward, integrate this forward, and then just integrate back, and you'll find that that this whole scheme is indeed reversible. Now, the mappings itself, the mapping from tau to tau plus epsilon at 2 or tau plus epsilon, we can represent them in this form here. We go from theta and p to theta and p plus some function of epsilon, right? And likewise for theta here, you can see that the mapping consists of theta and then some function of p. And so if we take the Jacobian of these transformations, so if I take the derivative of this mapping with respect to theta and p, right? So if I take the derivative of this with respect to theta, I have 1. The derivative of this with respect to p is 0, so I've got 1, 0. And then this with respect to theta, I have f dash theta. Then with respect to p, I have 1. I take the determinant and it's just equal to 1. So it preserves volume. And likewise with this here. So just by using this Stormer-Verley integrator, we've got an integration scheme that is volume preserving and reversible. So that's good. So now we've got a way of numerically solving any Hamiltonian defined from any target distribution of interest. But, as our friend from the US has said, this is still all deterministic. So we still haven't quite got to the stage of defining a Markov process. So how do we do this? Just one other point I should make is that although this integration scheme preserves volume and is reversible, what it does not preserve exactly is the total energy. So H at theta, tau, and p tau is going to be different from theta, H at theta, tau plus epsilon, and p tau plus epsilon. And that difference is the integration error. And this is an order, a squared order of error. So if we are lucky, or if we're smart, right, by choosing the step size in such a way, we can control the level of the error. And that means we can control the acceptance probability of this proposed move. Okay. Yeah, so the error, the integration error is going to be determined, as I said, by the step size and the number of integration steps. Right? So the error is going to accumulate. Right? But they can be tuned either manually or automatically, and work is being done by various people on trying to automate this. But we need an additional step for exactly the reason that has been highlighted. Everything is deterministic at the moment, and that's no use. The way that we make this a Markov process is by sampling the momentum from its normal distribution. So if you remember way back, we said that this momentum is defined as a normal distribution. Right? And so what we can do, if you remember our Gaap sampling scheme, what we can do is we can sample the momentum from the normal distribution, which would be the exact conditional of P given theta. And so here it is here. So given a particular point theta in the actual configuration space, we would sample the next value of P from the exact conditional. But it turns out that the exact conditional is independent of theta. So in other words, we're just making a random draw of P from the normal distribution which we gave it when we introduced it to the overall scheme. Right? So we draw a sample of P from this normal with this mass matrix M. And then we draw a sample of theta given P from this distribution here. And what is this distribution? Well, this distribution is nothing more than what we've just described here. It's the Dirac mass associated with the move by integrating this scheme here. So the integration is going to transform the smooth scheme to something that looks like this. Okay? And of course, what's happening is that we are accumulating error as we go along. But it has a Dirac mass. That's mine. And so we now have, this is a deterministic component, right? So we have a random P, so we sample P randomly. We then deterministically integrate theta and P to a new point in the phase space. We accept or reject it. We then sample P again, so that takes us to somewhere else in the joint space. We then integrate. We accept or reject. We then sample again, so we make another jump in the overall phase space. And what is happening, if you think about it, if I said this was my theta and P space, then what happens is that I make a random draw from the normal with zero mean and mass m, right? So let's just say this is 0. So I take some value of theta. I then take this point, sample from this here. Well, this is just a Dirac mass under the deterministic integration. Right? I accept or reject that. Let's just color this in. I then make another draw from my momentum, so let's say it takes me to here. I then update theta and P by doing this integration. Let's say I randomly stop there. I accept or reject that. I then draw another theta, move to here. I then integrate again, and so forth. So what you see is happening is that the deterministic component, this component here, is moving us along these isocontours in the joint space, and the random draws from of the momentum from the exact conditional is then jumping from one energy level to another. Or in other words, it's jumping from one region of density in the joint distribution to another. And what we then now have is a Gaap sampler, right, which will converge to the joint distribution of theta and P. And therefore, the marginal distribution of the thetas is the P theta that we're interested in. And what this means is that these integration steps and the approximate conservation of the Hamiltonian under the Stormer-Verley integration means that we can make potentially very large moves in our target space, right? So we could propose very large moves, and they could have a very high probability of acceptance. And this is the holy grail, right, of sampling methodology. And this is really cool. Why don't I give you a little working example which hopefully should clarify things, and then we'll stop. Actually, what time do we finish at? 1:30. Right. We'll just stop for a few questions and a bit of a breather to understand, just to kind of soak all this up. So here's an example. Let's say that our target distribution is this bivariate Gaussian that I introduced earlier on. Okay, zero mean, and it's got a covariance structure which is determined by this correlation coefficient rho. So we can tune it so that it's this kind of cigar shape. Right? So for rho being very large, we know that sampling from this distribution, either by Metropolis Hastings, is going to be really challenging, and we know that with Gaap sampling, we're going to have to drink lots of coffee before the sampler actually converges, and then we're going to have to wait even longer for it to get reasonable samples from the overall support. So this is a very benign looking thing, but it's extremely challenging. So if we define the Hamiltonian, so what's our target density? Well, it's this here. And if we take the log, the negative of the log of this Gaussian, we end up just with this here. Right, so this is our kinetic term, if you remember. So we're going to try and sample x's from this here. And then we have our momentum term, right, our auxiliary variable. Now, we've got this mass matrix. Now, I'm just going to say that, I'm going to arbitrarily say that the mass matrix is just an identity. Right? So that means that the kinetic term is just going to be P transpose P. So we've got unit mass. Okay? So that's our joint likelihood. So if we want to be statisticians or machine learning people, this is the negative of the joint likelihood, right, where this is the variables that we're interested in under our model. And these are the auxiliary variables. And from the physical perspective, this is the overall total energy of our Hamiltonian system, where this is the potential field and this is the kinetic energy associated with the dynamics. Now, it turns out that we can actually solve Hamilton's equations for this exactly, but I haven't done that here. What I've done is I've used that little integrator that I showed you earlier. And here is an example where I've set the step size to 0.18, and I've set the number of times that I call the integrator to be 20. So I ripple through the integrator 20 times. And here's the path. Now, this is in the, I've used theta here, and I should have used x. Right? So I'm starting at minus 1.5 and minus 1. So I'm starting here. And my integrator, right, with those 20 steps, meanders along here till I hit 1.5 and 1.5. Well, this is quite something, because what I've done is I've pretty much moved from one tail to the other. Now, the momentum, okay, the p-value, it kind of jiggles about like this, and it's kind of meaningless. Well, it's meaningless because we're not using the correct geometry, but we'll come on to that after the break. But anyway, it's doing something. But what's interesting is if we look at the value of the total energy, again, if we think of this as the negative of the log of the joint density, so at the start, the Hamiltonian has got a value of, what's that, 1.98, 1.88, whatever? And at the end, what's it got? Well, it hasn't really deviated much from it, so the error is pretty small, which means that the exponential of the negative of that error is going to be close to 1. So with almost probability 1, we're going to accept this enormous move across here. Now, this would have killed you if you tried to do it with Metropolis random walk. Right? It would have aged you if you tried to do it with the Gaap sampling scheme. And yet, in one proposal, right, you're getting a near acceptance probability of 1. Now, isn't that awesome? Yeah? So let's look at, let's actually look at it in action. This is 2 parameters of quite a complex model that I'm going to introduce later on. It's a stochastic volatility model that's used in finance. And it's a notoriously complex model because it has a latent dimensionality of a few thousand, and it's a hierarchical Bayesian model which introduces further challenges, which I'll discuss later on. But in this case here, I'm using a standard Metropolis random walk. The proposal has been very, very carefully tuned, right? So a PhD student aged considerably trying to get this tuned. So it's got an acceptance rate of about 25%, which is the sort of acceptance rate that is suggested by some asymptotic theory. And you can see that the random walk does, something sensible. It starts off in this region of low density, and then every 4 proposals, one of them is accepted, and it makes a nice random walk, and then it converges to the invariant distribution. Well, the chain converges, and it starts to sample from the high density regions. These here are the gradients. Right, so you can see that the random walk is reacting to the gradient information, because remember, if the proposal is such that it moves into a region of higher density, it's going to be accepted with probability 1. Okay? So that all looks good, and you can see once we've converged, then we're accepting all these proposals with a rate of 25%. So that means we've got 25% efficiency in the number of samples that we've been able to draw from our target distribution. So that's not so good, but nevertheless we've got there, and we're being able to sample from our invariant distribution, from our desired posterior. Well, that's all good. So what if we use this Hamiltonian malarkey? Well, look at that. Isn't that awesome? So we start at the same place, and then in one step, one proposal, it jumps up here, then it kind of jiggles about a bit, and I'll tell you why it does that later on. And then it converges, but look at the acceptance rate. 95%. If we had an acceptance rate of 95% with a random walk, then we'd be making very small proposals. And be moving very, very slowly. Here look at the size of that. And then when we've converged, look how densely we're being able to sample. And again, a very, very high acceptance rate. So this just looks magic. It's great. So before we finish off then, let me say that this deterministic proposal under the approximate flow of the Hamiltonian dynamics ensures a greater efficiency over a metropolis random walk. I mean, there's no doubt of that. But there's a small fly in the ointment. Can anyone think of what that fly in the ointment might be? Whoa, that was fast.
I'm guessing multimodal.
It's multimodal. That's a big fly in the ointment, and we'll come to that on Friday morning. Small fly in the ointment. Well, I neglected to talk about the matrix M. And remember when we were talking about the Langevin diffusion and the preconditioning? We had to stick in this matrix M, and who knows how we would select that? Who knows how we would tune it? Who knows how we would adapt it? Well, it turns out that the matrix M, the mass matrix for the hybrid Monte Carlo, the Hamiltonian Monte Carlo, turns out to be absolutely essential for efficient performance of HMC. And why is that? Well, it turns out to be because the diagonal elements of M, right, they reflect the scale of the random variables in the coordinate system that we are working in. And the off-diagonal elements, of course, are going to capture the correlation structure of the target. Now, you might say, well, we can do, and people have said to me, well, we can just scale the data. Well, that's fine if you're doing something trivial like probit regression or linear or logistic regression or what have you, where there's a direct tie to the posterior distribution of the parameters or the variables of interest and your actual data. But for most of the interesting models, that link is highly non-linear. It's completely unintuitive what it is, and so it's not clear how you would scale the data to obtain some sort of matrix that is going to scale your coordinate systems in an appropriate way and then rotate them to break up this correlation structure. So we need knowledge of the target density to set M, and we can do this by extensive tuning via pilot runs and so forth. And this is one of the common reasons why HMC isn't really taken up in any non-trivial applications that are going to be seriously assessed for convergence and for quality of Monte Carlo error when inference is done. And that's a great pity. And people like Andrew Gelman, who's a big fan of hybrid Monte Carlo, has been saying, well, look, why aren't people using this? Because they should be. This is great stuff. Well, we need to be able to resolve that weakness. And similarly with the Langevin-based sort of diffusion proposal mechanisms, we need to be able to select the precondition matrices, or we at least need to be able, well, better, be able to tune them. So can we resolve this weakness and do it without resorting to any ad hocery, but do it in a very systematic, principled way where there is a consistent theoretical framework that would allow us to do things that would be sensible, would stand up to the scrutiny of peer review, and would be actually useful? Well, gladly the answer is yes. And sorry, do we break for 5 minutes? Yeah. So do you want to break for 5 minutes now, and then we'll come back in and I'll see how far we can get on with the other stuff. Any questions?
So how do you choose the parameter of how far you integrate, the number of steps?
So epsilon and L. So epsilon, the integration step, and L, the number of integration steps, you can do that by tuning, right? But there's been some really nice work coming out of Andrew Gelman's team where they've actually done some really cool stuff where you don't even need to bother tuning that. It's done automatically. But the other thing is that you could say, well, epsilon and L, I'm going to make them random variables of my scheme, and so I will sample those. So you could actually just sample them as well, and that's another way of getting around that issue of how do you tune these. You sample them, right? But they are minor issues in comparison to M. Yes?
Wouldn't Fisher information matrix give you some idea about how...
You go to the top of the class, son, right? You are jumping ahead, or you've looked at the slides. Absolutely, and that's a great insight. And come and see me later. I might have a job for you in London. Any other questions? Yes.
The oscillating variable P is sampled from normal distribution.
Yeah.
Is there any reason it has to be normal?
Okay, that's a very good question. The auxiliary variable P is sampled from a normal distribution. Is there any reason why it should be sampled from a normal distribution? Well, the answer is yes and no. So first of all, P, the log of P, whatever the density has to be, is going to have to be quadratic to ensure that the physical interpretation is satisfied. So as long as the energy is quadratic, then you could use any density you want, provided that there's a quadratic energy term. So you could use a student T distribution. And you can have these nice big heavy tails, but still retain the quadratic term. Any other questions? How many of you are completely lost? Okay, that's one. I mean, please don't be shy. I've heard Bernard's talk yesterday was the first time I'd really understood learning theory, and Neil's a very good one for actually admitting that he doesn't understand things fully as well. So don't, if we don't understand things, we don't understand things. How many of you don't really understand what we've gone through? So that's about half of you. Okay, right, so what we're going to do after a 5-minute break, as we're going to look and see how we can actually resolve this weakness.